Hi everyone, in today's video we're going to focus on epoxides, a specific subset of ethers. We're going to learn about the properties, the preparation of epoxides, and then we're going to focus on one reaction, which is the ring opening of epoxides in the later half of this video. It is my hope that by the end of today's video, you'll be able to prepare epoxides using two synthesis strategies. One is the peroxidation of alkenes, and the other is the Williamson ether synthesis. And then you'll be able to predict reagents and products for ring opening of epoxides. You'll be able to predict and propose curved hour mechanisms of this particular reaction. So as opposed to the acyclic ethers that we've learned in the past, epoxides are in a ring, and they're specifically in a three-membered ring. And this is actually the cause of the fundamental difference between epoxides and the rest of your ethers. So if we start with the carbon-oxygen angle, that angle should be around 109 for your acyclic ethers, given that's an sp3 carbon. But in your epoxide, you're now in a three-membered ring, and so you are compressing that angle to approximately 60 degrees. Now let's see how this affects the electronics around epoxides. We're going to focus on dipole moments first. So while both the epoxides and the acyclic ethers have the same kind of dipole moments of bond dipoles, where you have your carbon-oxygen bond dipoles, for the acyclic ethers, however, those CO bonds can rotate, and this rotation would reduce the overall molecular dipole, because in some conformations, these dipoles will start to cancel each other out. However, in your cyclic ether, specifically your epoxide, those CO bond dipoles are fixed. They're fixed in a particular direction, which will on average be a larger overall molecular dipole towards the oxygen. So while the dipole moment in acyclic ethers are relatively weak, your epoxides have pretty strong dipole moments. And so for these two reasons, one where you have a very strained molecule in your epoxide and you have a pretty large or relatively large dipole moment towards the oxygen, your epoxides are typically fairly reactive, while your acyclic ethers have really low reactivity. And so because of this unique reactivity of your epoxides, we tend to use these in synthesis. And so now we're going to focus on preparing epoxides, and then we'll focus on how we can then use epoxides in synthesis. So there are two ways to prepare epoxides that we know now. One is the peroxidation of alkenes, where you take an alkene, treat it with a peroxy acid, and that will give you an epoxide. And the other is the intramolecular Williamson ether synthesis from a halohydrin, where you take a halohydrin, treat it with a base, and that would actually, in an intramolecular fashion, form your epoxide. Okay, let's start with our peroxidation reaction. So this reaction we have seen in the past, it requires a peroxy acid, and they are typical peroxy acids that we use for this specific reaction. One is your metachloroperoxybenzoic acid, otherwise short formed as MCPBA. And the other is your peroxyacetic acid, which is essentially just the CH3 version of your R group connected to your peroxy acid functional group. So if you see MCPBA, for example, in a problem, just know that it is a peroxy acid and it's used in your peroxidation of alkenes. Okay, so the mechanism of this reaction proceeds actually in one step with multiple arrows, and this is more of a review that you've seen before. You have your nucleophilic attack of your peroxy oxygen in red by your alkene, a loss of a leaving group, which is a carboxylate group, and then you have your proton transfer to the oxygen that used to be double bonded to the carbon, and then a nucleophilic attack back to one of the vinylic carbons in your alkene. Okay, so this is a fairly complicated mechanism, but it's nucleophilic attack, loss of a leaving group, proton transfer, and then another nucleophilic attack back to the alkene. And tracing your curved arrows, you will get your epoxide as your product, and a carboxylic acid as your byproduct of the reaction. So the peroxidation of alkenes is a stereospecific reaction, which means that the stereochemistry of the alkene essentially translates into the stereochemistry of your epoxide that you form. For example, let's say we wanted to do a peroxidation reaction on this alkene with two R groups, where the R groups are on the same side of the alkene. You would end up with your epoxides in which those R groups are also still on the same side of the epoxide. So cis alkenes will give you cis epoxides for peroxidation. And likewise, trans alkenes, peroxidizing them will get you trans epoxides. Okay, and secondly, you can also form an epoxide from a halohydrin. And we established that we simply need to take a halohydrin, treat it with a base, and you should get your epoxide. However, your halohydrin can also be synthesized from the reaction of an alkene in the presence of Br2 in water. And so your synthesis is typically actually in two steps. First of all, we try to form the halohydrin from an alkene, and then we form the epoxide from the halohydrin in our intramolecular Williamson ether synthesis. And so in summary, you take your alkene in your step one, treat it with Br2 in water, and in your step two, you treat it with a base. And typically you can just treat it with sodium hydroxide in water, and this would actually end up forming your epoxide. As a refresher, the mechanism of this reaction starts with your alkene with Br2, and you have a nucleophilic attack of that bromine from the alkene, loss of a leaving group, and then a nucleophilic attack from the bromine you just attacked back to the alkene, one of the alkene carbons. And this leads you to your cyclic bromonium intermediates that we've already talked about in the past, which can then be opened up by water, which will form your protonated product, which can be readily deprotonated by another molecule of water, which gets you to your halohydrin. So that's your first step. Then in your second synthesis step, when your halohydrin is treated with a base, such as sodium hydroxide, you can expect a proton transfer, which now ends up activating the nucleophilic end of your halohydrin, which means you can imagine an intramolecular SN2 to form your epoxide and a bromide as your leaving group. Okay, so just like in our peroxidation strategy, our second strategy, which involves forming your halohydrin and doing an intramolecular Williamson ether, is also a stereospecific reaction. Which is to say, if you started with your cis alkene, so in the case where your R1 and R2 groups are on the same side, you treat it with Br2 in water as the first synthesis step, and then in your second synthesis step, you treat it with sodium hydroxide and water, so you're doing your intramolecular Williamson ether synthesis from here. You will also end up with your cis epoxides as your product of this reaction. And if you follow each step in your synthesis, you would understand why. So in that first synthesis strategy, or in that first synthesis step, you have an anti-addition of your Br and your OH on the alkene. So you end up with your Br and OH being on the opposite side. And that actually happens to be the correct orientation of your Br and OH to do an intramolecular SN2. And so no rotation of the molecule is needed in order to then do your effective SN2, which is a backside attack, to form your epoxides. And so your stereochemistry kind of gets retained from the alkene all the way to the epoxide. And of course, likewise, if you had a trans alkene, you would end up with your trans epoxides as your major product in your intramolecular Williamson ether synthesis strategy to form these epoxides. Okay, so now we're going to focus on the rest of this video on the ring opening of epoxides. And there are two synthesis strategies in which we open up our epoxides. One is under basic conditions, which actually means that we try to create really strong nucleophiles in our solution to actually open up the epoxide. And so alternatively, you can indeed treat this epoxide under acidic conditions. And in this case, we actually created really strong electrophiles. And so here we take our epoxide, we still treat it with a nucleophile, but now under acidic conditions, and you would also here end up successfully opening up the epoxide ring. So we're going to focus on these two for the rest of the video. We'll start with the basic conditions. Okay, so here's an example of epoxide ring opening under basic conditions. You treat your epoxide with, in this case, a methoxide anion, so NaOCH3, and then you treat it with water and you will get your ring opened epoxide. Please note the location of your nucleophile and how it's added onto the ring. Much of this reaction can be readily explained by looking at the accepted mechanism for this process. You start off with an epoxide. Treatment with the methoxide, you have a really strong nucleophile that is strong enough to open up your epoxide ring without even activating the epoxide in any way in an SN2 fashion. Which now, if you add your second reagent, which is water, you can then neutralize your product in a proton transfer step to form your epoxide. And there's your mechanism. So now we're going to focus on our regiochemical outcomes for your ring opening under basic conditions. And we're going to use this particular example. You take now this asymmetric epoxide with a primary carbon on the right-hand side and a tertiary carbon on the left-hand side. You treat this asymmetric epoxide with your strong nucleophile, which is your cyanide, your Cn minus, and then you treat it with water. And because this is an asymmetric alkene, you can actually predict potentially two products from this particular reaction. The cyanide might attack the primary carbon or the tertiary carbon, but it turns out there's only one major product where the cyanide adds on to the primary carbon in this particular reaction. And the explanation for this regioselectivity can be readily explained by looking at the mechanism for that ring opening step. So what I've shown here are two different mechanistic outcomes, one in which you attack the primary carbon, that's the one on the left, and the one in which you attack the tertiary carbon, that's the mechanism on the right. And you can see that if you attack the primary carbon, you would lead to the major product, but if you attack the tertiary carbon, you will lead to the minor product. And the regiochemistry can be readily explained by thinking about your SN2 rules. So if you attack the tertiary carbon, you're attacking a more sterically hindered carbon or electrophilic center, which would be higher in energy than attacking your primary carbon, which is more accessible. And so your regiochemistry for your ring opening of epoxides is very much underlined with your SN2 rules, in which your nucleophile would prefer to attack the less substituted carbon in your epoxide. Okay, and so now we're going to focus on the stereochemical outcomes for your ring opening of epoxides under basic conditions. And for this particular example, I'm using this epoxide in which one side is a secondary carbon, the other side is a tertiary carbon. But both of those carbons are chiral centers. So you treat that with your SH minus, and then you treat it with water. And it turns out there's really only one major product of this reaction. And your major product has your nucleophile attacking the secondary carbon. We've already established that by the regiochemical outcomes in the previous scene. But importantly, what you also see here is a stereochemical inversion at the chiral center in which you attacked. And that's your major product. And once again, you can readily explain this by focusing on that ring opening step. Here, you have your SH minus nucleophile attacking the secondary carbon in an SN2 fashion. And recall that for your SN2, the nucleophile attacks at the backside with respect to the leaving group, which in this case is your epoxide oxygen. And so if your sulfur nucleophile is attacking from the backside, with this particular stereo configuration of your epoxide, you should expect your SH to add on from behind with respect to your OH on your ring. And so you should expect, in many ways, a trans configuration of your OH with respect to your nucleophile. Okay, so to put it all together, what we're going to do is take the epoxide which is drawn in the middle. And we're going to treat it with a variety of common nucleophiles that we would use to open up our epoxide ring under basic conditions. So we use our sulfur nucleophiles as our first one. So we've already discussed, you take your sulfur nucleophile, you attack this asymmetric epoxide. Note that it is asymmetric in the case that you have a secondary carbon and a tertiary carbon connected to the epoxide. So in this case, you should expect one, the regiochemical outcome, where the sulfur adds onto the secondary carbon, and an inversion of configuration. And so your product should look like what we're seeing here. Please note that R just means any alkyl group on that sulfur. Now with our oxygen-based nucleophiles, a similar trend is seen. You're just replacing the sulfur with an oxygen, but you still get the same regiochemical and stereochemical outcomes. The same goes for our cyanide nucleophiles, where your major product should look like what I have drawn here. And lastly, I wanted to introduce this particular concept, but you can also use your lithium aluminum hydride as a hydrogen nucleophile. We already discussed this in the past, but you can use it to open up your epoxide ring as well. So once again, think about it just like your other nucleophiles. The hydride nucleophile will attack the secondary carbon, and you end up with an alcohol that looks like this. I'm only showing you the hydrogen that added as a nucleophile just so you're aware that once again, it's still a stereochemical inversion if it were a stereocenter that we were actually forming in our product. Okay, and so lastly, we're going to go over the ring opening of epoxide, but now under acidic conditions. So here's an example. You take an epoxide, and now we treat it with HBr. So HBr is obviously a very strong acid. But what actually happens is that the ring opens up and the Br from the HBr adds on to that epoxide. So how does this reaction work? Well, so we've sort of seen this before. When your epoxide is under acidic conditions, just like other oxygen-based nucleophiles, you would expect that the oxygen is going to get protonated by a strong acid in your proton transfer step to form this highly activated epoxide. So this would be your epoxide now with a positively charged leaving group on it. This is a highly activated electrophile when you start looking at the ways in which this molecule could actually exist in equilibrium. With the leaving group rocking back and forth between both carbons it's connected to, given how strong of a leaving group it now is, each of those carbons bonded to the oxygen is now going to be significantly electron deficient. And that would make those spots very electrophilic. And then your Br minus can simply attack one of those carbons bonded to the oxygen in an SN2 format to form your product. That's your ring opened product. Okay, so now we will go over the regiochemical outcomes for this particular reaction. It's a little bit more complicated than your reaction under base conditions. Here, there are two scenarios. In the first scenario, you have an asymmetric epoxide where one of those carbons is a primary carbon and the other is a secondary carbon. And then in the second scenario, you have any asymmetric epoxide where one of your carbons is a tertiary carbon. Both of these will have two different regiochemical outcomes, so we'll go over each of them one by one. Okay, so here's an example of the first scenario in which you have an asymmetric epoxide with a primary carbon on one side and the secondary carbon on the other side. Now, you treat this asymmetric epoxide with methanol, which is your nucleophile, under acidic conditions. Just like your scenario under basic conditions, it turns out this also adds on to the less substituted side of your epoxide, so in this case, the primary carbon. And once again, the explanation can be readily seen by looking at the mechanism, where once again, you have your epoxide under acidic conditions, where your acid can be readily thought of as your protonated methanol. And so your first step will be the activation of your epoxide in a proton transfer step, which can now be readily attacked by your methanol preferentially on the primary carbon in an SN2 mechanism. The protonated product can be readily deprotonated by another molecule of methanol to then form your product. So the regiochemical outcomes could be readily explained using your steric effects that you typically see in SN2 reactions, where the nucleophile preferentially attacks the primary over the secondary carbon in order to minimize steric hindrance. Okay, so now in our second scenario, so scenario B, where you have an asymmetric epoxide with one tertiary carbon bonded to that oxygen. So here's an example. And we treat this asymmetric epoxide with water, your nucleophile, and in acidic conditions, which is your H plus. So you will, once again, get your nucleophile adding on to your asymmetric epoxide. However, please note here that your nucleophile added on to the more substituted side, which is your tertiary carbon, and not your primary carbon, which is the opposite of what we would see if you had a primary versus a secondary carbon, for example. Okay, and so what you should do is, as your practice, to propose your curved arrow mechanism for this reaction, now taking your epoxide to this particular product as your major product. But to explain the regiochemistry, we only need to think about a specific intermediate that is formed in this reaction. And that key intermediate is your protonated epoxide. So recall that your protonated epoxide is highly activated, and that oxygen is now a really good leaving group. And so the more realistic scenario here is you have your oxygen really wanting to leave on from both sides of those carbons that it's bonded to. And so on average, you actually have some carbocation character on each of the carbons connected to that oxygen. However, tertiary carbocations are particularly stabilized over primary or over secondary to the point in which that particular carbon, the tertiary carbon, becomes pretty electrophilic, which is where your nucleophile ends up attacking. And so in this case, the electronic effect of the carbocation character for your tertiary carbon is the dominant factor that dictates the outcome, the regiochemical outcome of this particular reaction. Okay, so I have written out here kind of a summary of your regiochemical outcomes for your acid catalyzed ring opening of your epoxide. So in summary, there are two scenarios. The first scenario is on your left. You have a primary versus a secondary carbon connected to your activated epoxide. In that scenario, the nucleophile attacks the primary over the secondary, and we've already talked about how that's because of your SN2, typical SN2 effect, where you want to attack the less substituted carbon because it's not very sterically hindered. However, if you're dealing with epoxides with tertiary carbons, now your dominant factor here is your electronic effect of your activated epoxide, where your tertiary carbocation character is particularly stabilized, and so that will be the more electrophilic spot, if you will, in your activated molecule. And so the nucleophile will attack the tertiary carbon over the primary or the secondary carbon in these reactions. Okay, and then we're going to finish this up by looking at the stereochemical outcomes of your ring opening under acidic conditions. So I've put in my prototypical epoxide here, where you have your epoxide where you have two of the sides are chiral centers. I have specifically denoted the configuration of the more substituted side, which is your tertiary carbon, because we already know that's where your nucleophile is going to attack based off of what we just discussed in the previous scene. And so treating this epoxide with HCl, your chlorine is going to be your nucleophile, and your major product is that shown here. And once again, note that in this case, just like in under basic conditions, the ring opening, if you're dealing with a chiral center that you're attacking, it inverts the configuration at that chiral center. So you went from an S configuration to an R configuration in this particular ring opening mechanism. And once again, the explanation can be readily seen by simply looking at the ring opening step of your reaction. And so after you have formed the activated epoxide, treating that epoxide with HCl, now your nucleophile is going to attack the more substituted side of that epoxide, as we have seen in this particular scene. And because it's an SN2-like attack, you would once again have your backside attack be the dominant trajectory for this reaction, and that would lead to the inversion of configuration at that chiral center. And so in this case, your epoxide was wedged, and so your chlorine is going to come in and be dashed on the ring. Okay? So that is that for your ring opening of epoxides under acidic conditions. Okay, so in summary, what we have done so far is we've learned of two strategies for preparing epoxides, so through peroxidation of alkenes and through an intramolecular Williamson ether synthesis from a halohydrin. And then we figured out there are two ways to open up epoxides using under basic conditions or under acidic conditions. Either one of those will get you to an opened up epoxide, but there are some regiochemical outcomes here that are a little bit different based off of the conditions in which you are doing your ring opening. So it's important to take note of that specific aspect of the ring opening mechanisms. Okay, so thank you so much for watching this video, and I will see you in class.